So today I'm going to show you how I derived pi with the group of people. So first we started off with a triangle inscribed within a circle with the radius 1, and we found the area of that, which we did by doing 1/2 base times height, and the area was 3 root 3 over 4. And then we found the area of a triangle circumscribed about a circle with radius 1. Did it the same way, 1/2 base times height, and we got an area of 3 root 3. And the next thing we did to derive in the process of deriving pi was we took a square and circumscribed a circle about it. So we had a square inscribed within a circle radius 1, found the area of that with base times height, so root 2 times root 2, and that got us area of 2. And then we circumscribed the square about the circle radius 1 and did base times height, so 2 times 2, and that got us an area of 4. And this we could do without any complicated formulas because we have a formula for calculating the area of a square, which is base times height, and for that of a triangle, which is 1/2 base times height. So next, we calculated the area of a pentagon inscribed within a circle with a radius 1. And so what we start off doing, you have a pentagon, and within that there are 5 equal triangles. And the angles of all the triangles are 72 degrees. And then split in half, you get 36 and 36 degrees. So you have a right triangle with angles 36, 54, and 90. And then what we did next was found the base of that triangle, which was sine 36. And we found the height of that triangle, which was cosine 36. And then we found the area of one of these triangles, which was cosine 36 times 2 sine 36, which was the whole base. And then to find the area of and then multiply by 1/2. And then to find the area of the entire pentagon, we did that times 5. So 5 times 1/2 2 sine 36, which is the base of a triangle, times cosine 36, which is the height. And so this equals 5 sine 36 times cosine 36. And what you may notice is that 5 is the number of sides, which is n, and 36 is, the angle 36 is 180 divided by n, so 180 divided by 5. And same with cosine. So we get this is where we really get the equation n multiplied by sine 180 over n times cosine 180 over n. So we can use this formula that we found with the pentagon to find the areas of any other inscribed polygons within a circle radius 1. Now we could have found this formula back with the triangles and squares, but it just wasn't necessary to use it then. It's more helpful with polygons 5-sided and up. And so here you can see, using this formula, we got an area of 2.378 for the area of the inscribed pentagon. And as you can see, it increases gradually. The more sides you have, getting closer and closer to pi. Okay, now to find the area of the pentagon circumscribed about the circle radius 1, we again find the area of a triangle, one of the 5 triangles, but this time it's a larger triangle because instead of being inside the circle, it's circumscribed about it. And to do that, we take sine 36 over cosine 36, which equals tangent 36, and then multiply that by 5, and that gets us the area of the pentagon circumscribed about the circle radius 1. And with the same formula, n tangent 180 over n, we can find the areas of all the other circumscribed polygons. And as you can see, this starts at a higher number, and rather than starting at a lower number, and then slowly increases to pi. Or no, sorry, slowly decreases to pi. And so at 10,000, we have almost exact, well, I mean, you can never get exactly pi, but pretty darn close. And then, so for example, here is a 100-sided polygon. And so I just drew one of the triangles. So we have theta, which is 180 over n. 180 over 100 equals 1.8. So this angle is 1.8. So that gives us tangent 1.8, which equals 0.031426, multiplied by 100, which gets us 3.142626, which is also very close to pi.